Okay, so we're going to do, you have the PowerPoint in front of you, 6 slides or so for net force and equilibrium, and we're going to watch this, go through these notes together. Have your calculator with you if you need to have a calculator with you also for this one. So the net force, this is something we've talked about already, this idea of a net force. It's all of the forces, the sum of all the forces acting on it. Keeping in mind that forces are vectors, so when we talk about sum, we have to do a vector sum. So, like in this picture right here that's shown, you can see that if I push 18 newtons to the right and 20 newtons to the left, the net force is going to be 2 newtons to the left, because you're going to subtract those two since they are in opposite directions. Or when you add them, another way of saying is when you add them together, you add a positive 18 and a negative 20, and you end up with negative 2 when you add those together. We could say that the net force is the one force that's replacing all the others that are acting on the object. So I could take away the pink and the yellow force here and replace it with just a blue force acting on this book, and that would have the same effect on the book. The book wouldn't know the difference. It sees that negative 2 newtons as the same as 18 and negative 20 together. So objects, the reason why I care about the net force is because it's going to tell me which direction objects are going to accelerate. Whatever direction the net force is, that's the direction it's going to accelerate. So this book would accelerate to the left because it has a net force of negative 2 newtons on it. So that's why we're going to care. So when we're worrying about what's the motion of an object, you need to know what direction the net force is, so you'll know what direction it's accelerating. So here's some different examples of net force. You should pause the video right now and go ahead and figure out the net force in each case here, and then when you start it up again, we'll go through them. Alright, so here is the net force for each of these. On this case, there's 8 newtons and 6 newtons together give you 14 newtons. 8 and 6 together, 14 newtons to the right. That's the net force. And since those both point to the right, you would add them up and give you 14 newtons. In this case, to the right of that, 5 newtons and 4.5 newtons acting in the same direction would give you 9.5 newtons of net force. That would be our net force, what we would call F net. Okay. In this case right here, you have 1200 up and 800 down. So if I were to redraw that box right here, my net force would be an upward 400 newtons. Because it's 1200 minus 800. That would be my net force on that particular object. In this case, 800 down, 600 up would give me a net force of 200 newtons downward, or negative 200 newtons is another way you can say that. That would be the net force. And of course this one, 50 up, 50 down, those are going to balance each other out, and you're going to end up with negative 20 newtons to the left. So that's going to be your net force. Will be the 20 newtons to the left, because the two 50 newton forces balance each other. This last one, 55 and something, give you 30. So you have to figure out what are you going to have to pull against 55 so that your net force ends up being 30, and that would be 25 newtons. So the force for B would be 25 newtons. Alright, so that's just a little quick introduction into figuring out net force. If they're in the same direction, you add them. If they're in opposite directions, you subtract them, and then you know, you have to look at the problem and see. Here's some other examples for determining net force. So again, I'd like for you to pause the video, figure out the net force in each case, and if it's not in one direction or the other direction, if it's at an angle, you got to figure out what that is. I'm going to do one of them together with you. The rest of them I'm going to leave, we're going to go over in class tomorrow. So we're going to do this first one together. First of all, notice that the 300 and the 50 are together. So that gives you a total of 350 to the right and 100 to the left. So if I redraw this box, 350 to the right and 100 to the left give me a net to the right of 250 newtons. In the up and down direction, I have 200 up and 100 down, which give me a net force of 100 up. So the first thing I've done is I've gone ahead and figured out in the left-right direction and the up-down direction what the net forces are for those directions. Now the total net force is going to be the one vector that I could replace with those. So I'm going to use completing the parallelogram. recognizing that these are at right angles to each other. So this makes a triangle with a side that has a 250 side and a side with 100. And I can use the Pythagorean theorem, 100 squared plus 250 squared equals my net force squared, to figure out what the net force is. So you'll go ahead and do that. I don't have a calculator with me right now, but you'll figure that number out. That'll be your net force. The other thing you have to do is figure out this angle that the net force is at. So you can use tangent. The tangent of that angle is the opposite over the adjacent. So this is stuff we've done before. This should all be a review for you for figuring out both the size of the net force and the angle. You're going to do the rest of this for all of these other problems here, and we'll go over those in class tomorrow. So the last little bit of this is equilibrium. So equilibrium is a special case where the net force is 0. Anytime the net force is 0, then there is no extra force acting on it. All the forces balance out, so the object will not accelerate. So that's important to remember, that if the net force is 0 on something, that the object will be not accelerating. So what you're going to see is two different things. You'll either see the object at rest, that's one case where the net force is 0, or you'll see it moving at a constant velocity. So either one of those is going to provide a situation where the net force is 0 and a situation where we say the object is in equilibrium. So if you see something at rest, you know all the forces on it have to balance. If you see something moving at a constant velocity, you know all the forces on it have to balance because it's in equilibrium. Okay? And in order to maintain a constant speed for something, it doesn't take any extra force. It just takes a balancing of forces to maintain a constant speed on an object. So here's a situation where I want you to determine whether or not which of these objects is in equilibrium. Some of them you might be able to tell immediately. Like this one here, there's no way that's in equilibrium because there's only one force acting on it. Or something like this, where you have 50 and 25, you already know that there's going to be 25 to the right and another 25 upward. There's no way that one's in equilibrium. So you can start seeing which of these might be in equilibrium and which one won't be in equilibrium. So what I want you to do, and we'll go over them in class tomorrow, is I'd like for you to determine which of these objects is in equilibrium. And if it is, you can circle it, and if it's not, just put a big old X over the top of it if it's not in equilibrium. And we'll talk about it tomorrow.